It's kind of a intro to stats, but what we're most interested in here is to look at our random variables. There are lots of different variables that we study in statistics, and we want to say something about those numbers because that informs policies that might be made, laws, and so on. So we're always looking at statistics. Polls, big one right now, and I'll be following some polls. Right now, if you're following things, Joe Biden seems to have a pretty big lead on Donald Trump. All that stuff will change, probably slightly over the next several months, but we can track, various sites track what the likelihood is that someone's going to win. And right now, I think it's, they're predicting, based on all the polling that's been done, in various states, including Michigan, which is a swing state, as they call it, because you know, there are some states like New York and California that'll always go Democrat. There's some states like Montana and Wyoming that'll always go Republican, but there are some states that kind of go Republican sometimes, Democrat the other times. Those are called swing states. And as you know, the states determine via the Electoral College, the president's going to win. So they do all these predicting, and right now it's showing Joe Biden has a chance of about 3/4 that he's going to win the election. And a lot of things can happen. And you know what happened 4 years ago. Donald Trump was going into the election with a similar 75% to 25% likelihood that he was going to lose, and he ended up winning. But remember the way probability works, 25% chance of winning means there's a 1 in 4 chance. So it wasn't like Donald Trump didn't have a possibility of winning. He had a 25% chance of winning, and it just turned out to be the cards were in his favor at that time. So, but we need to know the variable, and there's different kinds of variables, and that's pretty much what I would like to talk about in this section 1.1 is the types of variables, because if it's a quantitative variable, you're going to use one kind of graph to present the data, and if it's a qualitative variable, you're going to use a different one. So we need to be able to identify, classify these variables, and that's going to be the big thing. All right, so the first way that we classify variables is based on whether they're numerical or not. And so for random variables, we have qualitative and quantitative. And I think we did a homework exercise where we kind of talked a little bit about this. Qualitative are numerical, and quantitative are numerical. Quantitative variables, think about the first part of that word, quantity. Ask the questions, how much gas do you typically put in your car? How much do you weigh? How tall are you? How much or how many? How many credits have you taken so far at Delta? How many cars do you own? How many TVs are in your house? How many siblings do you have? How many, how much, or how many? Those are numerical. If you were asked those questions, you would respond with a numerical response, a number. Non-numerical variables, well, you know, we can, your gender, okay, how would you classify your gender? You certainly wouldn't answer that question with a number, right? I'm a 7. No, that's not what we're talking about. You know, your religion. Someone asks you your religion, you'd say, you know, Christian, non-Catholic, or Christian Catholic, or Jewish, or Muslim, or none of the above. But you wouldn't answer those with numbers. So that's the big difference between quantitative and qualitative. All right, we can break this down further. There are 2 types of quantitative variables. So now both of these types are numeric. They're numbers, but with the kind of the how much question, we have continuous, numerical, random variables. And the kind that answer the question how many, this is not always the case, but usually this is the case. These are known as discrete random variables. And just to give you a sense of the the difference between these two numerical variables. Discrete are countable. That's the big difference. Can you count the number of items? How many siblings do you have? I can count them, 0 siblings or 1 sibling or 2 siblings or 3 siblings, 5 brothers, whatever. How many pets are in your house? Well, there's 1, there's 2, there's 3. You would never answer that question with, 1.5. I have 1.5 pets. No, it's got to be a countable number. That's the discrete. Number of siblings. Number of. If it begins number of, then you're probably dealing with a discrete random variable. Number of pets, number of cars you own, number of credits you're taking, and so on. Continuous is more about quantities that are not countable. So that's the big difference. So if someone said, how much gas? How much? How much gas did you put in your car this morning? Usually it's when the gas thing turns off, or if you turn it off after $5 or you turn it off after $10. And then you look at the amount of gas you have, and it's usually not a whole number of gallons. It's usually not 1 gallon or 2 gallons. It's like 6.59 gallons or something like that. So not countable. Amount of gas. Your height. How tall are you? Usually we would say, I'm 72 inches tall, or I'm 73 inches tall, maybe 6 foot, 6'1", something like that. But you can also be, 6'1 1/2, 6'1 1/3, 6'1 1/4. You can take all those measures between 6 foot and 6'1". Someone could appear at any point. In fact, if at one point in someone's life they were 6 foot, and at some other point they were 6'1", then they have assumed every height between 6 foot and 6'1". So there's this continuum of possible values, and that's where continuous comes from. Whereas if we drew the graph of the discrete, we would have something like this, where you could only have 0 or 1 or 2 pets or 3 credits or 4 siblings, or some countable number. Whereas continuous, it's like a subset of the number line. That's the big difference. All right, here's some problems. And what I'm going to do is maybe magnify that a little bit. Here's some problems that you would see on the MyMathLab site. And there would be multiple choice. There would be 2 radio buttons, one for quantitative, one for qualitative, and you just select the right one. So you can see a couple of those that we've already done. Let's take a look at number 17. And I want to try something here before you give me your answer. Grams of carbohydrates in a donut. All right. Do you think that that is a quantitative measure or a qualitative measure? Now, what I would like you to do is to go to the chat and type in your answer. But I don't want you to hit enter, because I'm going to go 3, 2, 1, and at the same time, everybody's going to enter their answer. Is this variable, grams of carbohydrate in a donut, is it quantitative or qualitative? Choose one of those and write your answer in the response. Okay, so here we go. On the count of 3, hit enter. 1, 2, 3, enter. Let's see your responses. What about phone number? Quantitative or qualitative? If you'd like, go ahead and write the answer in the chat. I guess that's a sample phone number there. All right. Okay, so now we have a difference of opinion here. I see some quantitatives and some qualitatives. All right, so even though the phone number itself is made up of numbers, it doesn't answer the question how much or how many. It's not a single number that you would report. So this is qualitative. All right, let's go over to discrete versus continuous. Here, let me give you a variable and ask you a similar question. Now, this variable is going to be numerical. It's going to be quantitative. The question is it discrete or is it continuous? And here is the variable. Water lost by a leaky faucet. Is that discrete or is it continuous? And you can go ahead and put it in the chat there to give me some feedback as to how you're understanding this. Okay, it looks like you have a pretty good handle on this. I mean, all of the responses are continuous, and that is the correct response. But these are going to be just multiple choice questions. So this particular one said, here's the variable water loss by leaky faucet, discrete, quantitative, or continuous quantitative. Yeah, that's the idea. Goals, we'll say soccer goals, scored in a season. So some of you might be soccer players. Number of goals scored in a season. I know somebody scored 7 goals in a season. So it's numerical. Is it numerical discrete or numerical continuous? Okay. Yes, this one is discrete because the fewest number of goals that someone could score in a season would be 0, but they could also score 1, and they could also score 2, and they could also score 3. We could actually count the number of goals that someone scored in a season. The other feature is that someone can score 2 and 3, but they can't score anywhere between 2 and 3. It wouldn't make sense to say someone scored 2 1/3 goals in the season. This doesn't work. Countable. Okay, so we are classifying variables here, and we're breaking them down by qualitative, quantitative, and then quantitative, we broke them down a little bit further than that. Now let's look at the level of measurement. Another way that we can classify variables is by their level of measurement. Now, you can think of level of measurement as being something like the degree to which the variable is numerical. On the numerical variable continuum, where does the variable fall? And so I'm just going to draw a number line to indicate a continuum. And over on the left-hand side, we have few or no numerical properties. And on the other side, you're going to have many numerical properties. And you can think about it this way. I mean, over here on the left where they have no numerical properties, if we're talking about variables now, what can you do with numbers? Well, you can order numbers from smallest to largest or largest to smallest. You can subtract numbers, that's meaningful. You can compare numbers by using a ratio, like the relationship between 10 and say 40 is that 40 is 4 times as big as 10. You can actually say things like this, and it's meaningful, and that would be more properties. Does the variable have a zero value, and if that variable has a 0 value, does that 0 mean none? That's another numerical property. All right, so here they are according to their order of numericalness. That's a word. We have nominal and ordinal and interval and ratio. Ratio level variables have the most number of numerical properties. Nominal level variables have the fewest numerical properties. Your questions on MyMathLab will be similar. Here's a variable, what is its level of measurement? And you'll have to select between these 4 possible answers. All right, so let's go ahead and define them. By the way, I'll be presenting one thing on these but the lecture notes, they actually have a listing of some definitions if you want to refer to that outside of class. So you might want to download those documents that I made available at the e-learning site. But there they are, nominal, ordinal, interval, and ratio. All right, the way that we're going to talk about the numerical properties, we're going to start from the left, and no numerical properties to speak of here. But they could be numbers. without numerical properties. So for example, the example that we use here is like a jersey number on the back of an athlete. They wear a number like 86 or something like that, or 13. Those are numbers, but they really don't have any numerical properties. We wouldn't even want to rank the jersey number 13 and the jersey number 88 and say, you know, one of those jerseys is larger than the other or anything like that. They're just ID numbers. It's the equivalent of writing AB on the back of a jersey. We certainly wouldn't say that the jersey number AB is numerical. So similarly, the jersey numbers would be an example of where you're using numbers, but they really don't have any numerical properties. Now, some of the things that I list here under nominal, the values cannot be ordered in a meaningful numerical way. And the reason I say that is because as we go to the next level of measurement, the next level of measurement is going to take on that number property that the previous category didn't have. So ordinal, if you look at the first part of that word, implies order. And in terms of the variables that we've defined earlier, we have qualitative and quantitative. It turns out that interval and ratio level data are quantitative, and sometimes ordinal variables are quantitative as well. Nominal level variables are qualitative, but sometimes they can be ordinal. So this might be a useful way of thinking about these levels of measurement. So the ordinal level of measurement is probably something that you've seen a lot before. First, second, third, and so on. Those are the standard ordinal values that we use. Indicates the order, but it doesn't indicate anything else. We could just use rankings like 1, 2, 3. So here's a 4 and so on. This is an example of where the variables are quantitative because we're using numbers, but it doesn't have other significant properties of numbers that we need to move to the next level. What about these? You recognize these? You recognize those? Those are what, movie ratings, right? Rated G, rated PG-13, and so on. We do know that if this is a scale that identifies child friendliness, that the friendliest movies are over here in the G, and the least friendly movies to children are over here on the other side. But they are qualitative variables. They're letters, sometimes combined with numbers, but they definitely have an order to them based on kid friendliness. The key piece here is that the values can be ordered. Subtraction is not meaningful. And by that we mean this: if you took you know, second and subtracted first, second minus first, what does that mean exactly? Well, one place, but it doesn't have any numerical property. Also, if you're running a race, it could be the case that the first two runners were only like a half a second away in their speed, and then the third place finisher was 10 seconds behind. So the difference between 1 and 2 is like a half a second, but the difference between 2 and 3 is like 10 seconds. And so there's no real meaning behind from subtracting two of these adjacent possible values here. So subtraction is not meaningful. certainly PG minus G is not meaningful. It's clear there. But even with 1 minus 2 and 3 minus 2 and so on, not meaningful subtractions there. So values can be ordered, but subtraction is not meaningful. And again, we list that there because in the interval level variables, they are numerical and subtraction makes sense. However, at this level, the zero data value does not mean none. And two of the examples that we use here where subtraction makes sense, but the zero data value does not mean none, is with the year. The year today is 2020. 19 years ago, the year was 2021, or 2001, or 2001. And in fact, we can do subtraction, right? And if we do subtraction here, that's exactly how we figure out our age. We take the current year and subtract the year we were born, and then we get our age. So subtraction is meaningful here. Not meaningful over for the ordinal level variables, meaningful for the interval racial variables. But let's talk about the year 0. I guess that's how we would represent the year 0. Some think it has religious significance. This doesn't mean that there wasn't a year. There was a year. It was just the year 000. So that's what we mean when we say the zero data value does not mean none. There was a year. It's just that's how we label it, classify it. Subtraction makes sense. The other one is time. No, how about temperature? We did time. Temp. Now for the temperature, we can say, well, it's 80 degrees today and it's going to be 75 degrees tomorrow. We could actually do a subtraction, and the subtraction makes sense. In this case, it means that there's a difference in 5 degrees in the temperature. What it means. So subtraction makes sense. But what if we had 0 degrees? Does that mean that there was no temperature? No, it just means it's cold, right? So 0 is not kind of the starting first value. It's just kind of in a range corresponding to the level of mercury. So does not mean no temperature. All right, one last thing to state here, a property that it doesn't have, that the next category will have, is that ratios do not make sense. And here's what I mean by that. If you have, let's just look at a variable that we know is interval level, and that's the degrees. So let's say that we have 2 days. One day it's 20 degrees outside, and the other day it's 60 degrees outside. Could we use ratios in terms of so many times as many? So can we say that it's 3, since 20 is times 3 is equal to 60, can we say it's 3 times as much, 3 times as cold? No, probably not. You know, and if that doesn't convince you, if we go from 1 degree to 3 degrees, you know, is it 3 times as cold? Well, probably not. Ratios probably do not make sense here. Because this kind of this relative, you know, what does it mean to be cold? And what does it mean to be 3 times as cold? And then what if you went from -1 degree to 1 degree? I mean, then how would you represent a ratio in that way? So ratios, it's hard to say twice as much, 3 times as much in a context like when you're dealing with interval level data. All right, let's move to the final category, and that's the ratio level variables. In this one, the two properties that the interval level variables did not have, ratio level variables will have. So the zero data value means none. By the way, as we move along this continuum from no numerical properties to numerical properties, all of the numerical properties in the previous group get merged over to the next. But then the next group picks up additional numerical properties. The other thing is that ratios make sense. And when you think about ratios make sense, ask yourself the question, can I say twice as much and have it make meaning, have meaning in this case? Twice as much makes sense. It didn't make sense with our temperature example, but it's going to make sense here. All right, let me just give you an example. Number of siblings. Now we know that that is a discrete level quantitative variable. But if you think about all the possible values, how many siblings do you have? Well, if you're an only child, you might have none. You might have a brother and a sister, 3 siblings, 4 siblings, and families can get fairly large. So what does that value right there mean? That zero data value. Does 0 siblings mean that the person has no siblings? None? That's right. If you have 0 siblings, you have no siblings. So 0 means none. That's going to be a feature of a ratio level variable. And the other thing we should check probably is the ratios. If one student has 2 siblings and another student has 6 siblings, can we say that the one student has 3 times as many siblings as the other student? Would that make sense in this context? And the answer is yes, it does make sense in this context. So therefore, we're dealing with a ratio level variable. Take a look at some examples. You can see that we've done a couple here. Let's take a look at number 31. And again, as you do these problems, it's going to be multiple choice, so you don't have to physically type in the name of the level of measurements. It's just going to be a radio button next to nominal, ordinal, interval, and ratio. And so those are our choices. And which one would you select for the nation of origin? Are you from Russia or Greece or the United States? What's your nation? Nominal, ordinal, interval, or ratio? Go ahead and enter put your answer in the chat. Yeah, this is kind of the standard qualitative. You're all correct. This is nominal. Because all of the possible data values are names of countries. What about number 32? Movie ratings of 1 star through 5 stars. We see this a lot on Amazon and a lot of websites where they're ranking things or rating things, and people give a rating from 1 to 4. Okay, I've seen a lot of correct answers, and yes, ordinal. Okay, so 1 star, 5 stars, usually they indicate them like this, so they're not even really listed as 1s, 2s, 3s, 4s, and 5s, you know, and even sometimes they'll give you a kind of a half of a star. And so a lot of times it looks like that. Clearly not numerical, and so very few numerical properties. But you can't order them because a rating of 5 is much better than a rating of 1, let's say. Okay, there's a couple of other things that this is the very first section of the textbook where they're giving you an introduction to statistics, and so there's some additional definitions in here, and so a couple of things. A sample And usually we take a random sample versus a population. The way that I typically draw this is with a Venn diagram, and I say the population is, as an example, we could say all registered voters in the US. And let's say we want to say something about all the registered voters in the US. You know, for example, you know, what presidential candidate are they going to vote for? So we're interested in what the whole population sees because that'll determine the outcome of the election. But to predict this in polling, what we do is we take a subset. And the subset is the sample. It comes from the population and it's randomly selected. So a sample is a subset of the population. And usually when polling goes on, we take this sample and we say who you're going to vote for, and let's say it comes back that 49% plan to vote for Joe Biden, 49%. Now that number that we come up to in a poll, that's a number that describes the sample. And that number is known as a statistic. So if you have a number that describes the sample, it's called a statistic. And if you have a number that describes the population, it's known as a parameter. Most of the time when we're doing studies, we don't know what the parameter is. And the best we can do is take a poll and to estimate it. This process of inferring the results of a sample to a larger population is known as statistical inference. In our example, we wanted to infer that 49% of the entire population will vote for Joe Biden because we are inferring from the small sample where we got that result to the whole population. So all these polling that you're reading about right now, even though we have probably 200 million, over 200, no, it's probably closer to about 150 million Americans that'll be voting in the election coming up. Because that's the case, when they do these polling, all the polling results are based on about 1,000 respondents. So 1,000 respondents make up the poll and come up with this 49%, and they infer it to the larger population. And the beauty of the whole process is that it's accurate about 95% of the time. And one of the things you need to come to grips with as you study statistics is this variability in these polling numbers, and this whole notion of when you receive a polling number, it's correct 95% of the time, but it is incorrect 5% of the time. And you don't know when you do a poll which one you have, the correct one or the incorrect one. You just know probabilistically. Now, if you're just going to describe a group and you're not going to infer to a larger population, then we just call that descriptive statistics. So another thing that they talk about in this section is just to see the difference between descriptive statistics, where you're just describing a group, and inferential statistics, where you're inferring from a sample to a larger population. Okay, let's take a look at this idea of the difference between a parameter and a statistic. A parameter is a number that describes the whole population, and a statistic is a number that describes the sample when we're doing statistical inference. All right, so in a calculus exam, the average score for class, there were 28 students in the class, on the midterm was 72%. That number right there, a parameter is a number that describes the population, and a sample is also a number, but it describes a different group of individuals. Is 72%, as you see it in this context, in this example, is that a parameter or is that a statistic? When you're doing these problems, you don't want to read in more. You don't want to read in more to the problem than what's there. Now, here's another way that we could ask this question. Suppose a professor gave a randomly selected 28 calculus students, and the score turned out to be 72, and then they inferred the result of that midterm to all other students taking calculus. You see, in the second scenario, we were inferring from the smaller group, the sample of 28 students, to a larger group. That would be statistical inference. In this case, descriptive statistics are going on because there's no intent on the part of the professor to infer the 72% result to any larger group. There's nothing inferred here. So therefore, this must be the whole group, the whole population. And we're describing the entire population. And since it's a number that describes the whole population, this is called a parameter. All right, let's take a look at number 10. In number 10, a national survey on substance abuse of basically teenagers reported using illicit drug. 9.6% of respondents aged 12 to 17 reported using illicit drugs within the past month. And this is an actual study that was done, close to 10%. Is that 9.6? Is it a statistic that describes the sample, or is it a parameter that describes the whole population? And yes, looks like you are doing that one pretty well.